In this video, we're going to discuss fluctuations in equilibrium. So let's start with a box that has an imaginary partition in the middle, and we have an ideal gas inside this box. And I'm going to call N the number of molecules in the left half. And I'm going to call N prime number of molecules in the right half. And obviously, if I add these two numbers, n plus n prime, I'm going to get the total number of molecules, So I have n plus n prime is equal to n. And finally, I have V, the total volume. All right. So with my imaginary partition in the middle, the volume is divided into two, V over 2 on the left, V over 2 on the right. I have n molecules on the left, n prime molecules on the right, and the total number is capital N. And finally, I would like to point out that I have a isolation of this system. So this is going to be isolated from the rest of the world. So in terms of thermodynamics, what this means is the system cannot exchange energy with its environment. So let me note that here I have an isolated system that does not exchange heat with its surroundings. So that means I have no heat exchange with the surroundings. So the system is at thermal equilibrium. So what thermal equilibrium means is I have prepared the system and I have waited for a long time. There was a random distribution of these gas molecules, and at the end I find that more or less the number of molecules on the left and the number of molecules on the right will be the same. So that's going to be my thermal equilibrium. So the other property of the system at this point is it's at thermal equilibrium. That means we have waited long enough for the gas molecules to distribute evenly in this system. The system has been undisturbed for a long time. And what we find is that if you have capital N of the order of Avogadro's number, that means it is a very large number. What is Avogadro's number? 6.02 10 to 23 molecules. So that means I have a very large number, and therefore the system can be studied using statistical techniques. And what I will find at thermal equilibrium is that the number of molecules on the left, N, will be almost the same as the number of molecules on the right, and this will be of the order of capital N over 2. So this is going to be an important finding if I have a large number of gas molecules. So this is true if I have a large number of gas molecules. However, if I look at the system at all times, actually N is something that has slight time dependence. So it's a function of time. it's going to fluctuates in time. But the fluctuations will be centered around capital N over 2. Now the question is, are these fluctuations significant or not significant? Well, we're going to see that as the number of molecules N increases, the fluctuations become less significant. So the deviation from the equilibrium value, capital N over 2, will become less significant. And we can see this very easily. For example, here I have capital N is equal to 2, so very small number of molecules. You can see that I have both molecules on the left, second molecule on the right, on the left, first molecule on the right, first molecule on the left, second molecule on the right, and both molecules on the right. So you can see that it's very likely that I will have N is equal to 0 or N is equal to 2. So N can be deviating from capital N over 2, which is 1. There are two scenarios here. This scenario and this scenario basically give me a large deviation from equilibrium. So here I have N is equal to 2. Here in this scenario I have N is equal to 0, and in these two scenarios I have N is equal to 1. So there are four configurations, possible configurations for capital N is equal to 2, and the number of times I will see N deviates from N equals 1 will be quite significant. If I increase the number of gas molecules to 40, however, if you run a computer simulation of this and assume that you have a random motion of these gas molecules, you will find that this random motion of the gas molecules will make it clear that N will be close to 20 most of the time. If I actually take a picture of this random motion of molecules inside this box, I see that N will deviate from 20, which is capital N over 2. So this point, N is equal to capital N over 2 point. There are some fluctuations in time, but the fluctuations will be centered around capital N over 2, 20, and the amplitude of the fluctuations will not be very significant as compared to capital N is equal to 2 case. Now if you have N is equal to Na, a large number of molecules, now you will see that you have fluctuations in time centered around Na, but at this point the fluctuations will become even less significant. So this is least significant fluctuations. This is significant fluctuations case. All right, so it has now become clear that as the number of molecules increases, I'm going to have less significant fluctuations. Now, in the case of two molecules, you have seen that if I label these molecules 1 and 2, there are four possible configurations. Both molecules on the left, N is equal to 2. 2 is on the left, 1 is on the right, N equals 1. 1 is on the left, 2 is on the right, N equals 2. So I have two possible configurations. One configuration for N equals 1 and one configuration for N equals 0. Both molecules are on the right. Okay, so each distinct way in which the molecules can be distributed we're going to call a configuration. All right. So the number of configurations I have for the case of having 2 molecules is 4. So 4 configurations are possible in this case. If I have just one molecule, then I will have either the molecules on the left or on the right. So for one molecule, I have 2 configurations. One molecule, 2 configurations. 2 molecules, as we have seen, I have 4 possible configurations. And basically, if I have n molecules, capital N molecules, what is the number of configurations I can have? 2 to the power n possible configurations. Okay, so this is going to be important. Now I want to concentrate on the case where I have capital N is equal to 4. All right. So I have labeled these molecules 1, 2, 3, and 4, and I'm looking at the number of possible configurations. So I can have all molecules on the left. That means n equals 4, n prime equals to 0. The number of configurations, Cn, I call number of configurations. This is a function of the number of molecules on the left. That is 1. Now, this is one possibility. The other possibility is n equals 3. N equals 3 will correspond to 4 configurations. Now, molecule number 1, 2, and 3 are on the left. 4 is on the right. Left, left, right, left. Left, right, left, left. Right, left, left, left. Okay, so that is 4. Now, I can have 2 molecules on the left, 2 molecules on the right. How many configurations give me this scenario? For example, I can have left, left, right, right, left, right, left, right, left, right, right, left, right, left, right, left, etc. This gives me 6 possible configurations, as you can see here. If I look at the number of configurations I can have for n equals 1, that is, I have only one molecule on the left, that could be the 4th molecule, 3rd, 2nd, or 1st molecule, 4 configurations. All molecules are on the right, there's nothing on the left, that is 1 configuration. Okay, so I have the relative frequency of a configuration or an event. We call this the probability. So I denote this by probability for capital N molecules. And the probability of having the number of molecules on the left equal to the total number of molecules on the right becoming 0, is actually 1 divided by 2 to the power n, total number of possible configurations. So Pn is probability. And what is probability? It is relative frequency of an event. So it's the relative frequency of a configuration. So if I have n equals 4, as in this case, the total number of possible configurations is 16. So 16 possible events, configurations I can have. Now I'm asking, what is the probability for 4 molecules of having no molecules on the left side? N equals to 0. This is 1 divided by 16. What is the probability of having only one molecule on the left side? As you can see, there are 4 scenarios that give me this result. So it's 4 over 16, it's 1 over 4. What is the probability of having 2 molecules on the left, 2 molecules on the right? It is 6 divided by 16, so it is 3 over 8. What is the probability of having 3 molecules on the left, 1 molecule on the right? It's 4 over 16, 1 over 4. And the probability of having all molecules on the left is there's only one configuration out of 16 configurations, 1 over 16. So as you can see, if I add up all of these possible scenarios here, I'm going to end up getting 1 over 16 plus 4 over 16 plus 6 over 16 plus 4 over 16 plus 1 over 16, 10, 14, 15, 16 over 16, that is 1. So the sum of all the probabilities is equal to 1. So that means I have encountered all possible events. So basically, what am I doing here? The probability for capital N number of molecules of having a lowercase number n molecules on the left is the number of configurations in which I have n molecules on the left divided by the total number of possible configurations I can have. And that gives me the relative frequency of the occurrence of this event, and it's the probability of having n small case, lowercase letter, n number of molecules on the left hand side. And also I have seen that when I add up all the probabilities, I'm going to end up getting 1, so probability is normalized. So if I look at the probability of having for 4 molecules n much less than capital N over 2, which is 4 over 2, that is 2. Small n is much less than 2. For example, n is equal to 0, the probability is 1 over 16. So this probability is low. Now, as n approaches a very large number, Avogadro's number, 2 to n will become very large, right? 2 to the power this is going to be 2 to the power 6.02 10 to 23. It's going to be a very large number. So the probability of having, for Avogadro's number of molecules, n equals to 0, for example, will be almost 0, because this will be equal to 1 over 2 to the power Avogadro's number. Okay, so this probability will be very small. However, the probability of n becoming similar to Avogadro's number divided by 2 for total number of molecules, Avogadro's number, will be high. So this is going to be a large number. Okay, so you can see that for statistical analysis purposes, it's very important that we have a large number of molecules in order to come up with a statistically significant answer. All right, so let me summarize a few of these results. Probability for n molecules where the number of molecules on the left is much less than capital N over 2 or much greater than capital N over 2 is very low. And you can see that that means either you have all molecules on the left, for example, if it is n equals 0, or n equals the capital N, the other extreme case, all molecules on the right. That's a very orderly configuration. It's not a random configuration. So non-random or orderly configurations are unlikely. So the probability of having these configurations is very, very small, especially when n gets capital N is large in this limit. On the other hand, if I have for capital N molecules, looking at the probability of having almost the same number of molecules on the left and on the right, this is a random configuration or disordered configuration, we can call it. Such configurations are very likely. All right. For example, in the case of 16 molecules, the probability of having 2 molecules on the left, 2 molecules on the right, that's this case, that has the highest probability of all the possible scenarios I have. It's 3 over 8. And why is that the case? Because in order to have a non-random or orderly configuration, the molecules must move in a very special way in order to achieve a non-random or ordered configuration. Okay, this is because the occurrence of such an ordered scenario would mean that the molecules must move in a very special way to achieve an ordered configuration, which is unlikely. All right. And regarding the fluctuations, if we basically look at the fluctuations in time, so n is equal to number of molecules, the equilibrium value is capital N over 2, plus or minus some fluctuations. So delta n I'm going to call fluctuation amplitude. This is going to be depending on the number of molecules. For example, for one molecule, the fluctuation amplitude is very high, right? It's either 0 or 1 molecule on the left. For Avogadro's number of molecules, the fluctuation amplitude will be very small. The probability of having for capital N molecules a fluctuation so that n is going to deviate from total number of molecules divided by 2 plus minus delta n. This probability will decrease as the fluctuation amplitude that you consider increases. So that is to say, large fluctuations are unlikely. Okay, so how can I see this? Well, what is the largest fluctuation you can think of? Let's say that n is equal to n over 2, and then the fluctuation makes n equals to 0. Well, we have already talked about this. N equals to 0 for a large number of molecules is a very ordered configuration. It's very unlikely. Basically, as delta n increases, we're going from disorder to order, and that's why as you go from disorder to order, the probability decreases, so these large fluctuations will become very unlikely. On the other hand, if I consider the probability of having a fluctuation n is equal to n over 2 plus delta n, this is the same as the probability of having n equals n over 2 minus delta n. Positive and negative fluctuations are equally likely. For example, if you go back here, n equals to 4, the probability of having a fluctuation delta n is equal to 1 here. So I have n equals to 2 minus 1 or n equals to 2 plus 1. These two probabilities are both 1 over 4 and 1 over 4. So I have the same probability for positive or negative fluctuations. The other thing is, basically we can now solidify the description of thermal equilibrium. N is equal to capital N over 2 is a macro state of this system, is a macro state. And if you give me the position vectors of all of these molecules, so from here, for example, I have R1, R2, this is R2, this is R1, etc. So I can give you the position vectors of all molecules. R for all molecules is a microstate. Okay? So now we can talk about equilibrium. If you have a system of many particles of the order of, for example, Avogadro's number, whose macroscopic state or macro state does not tend to change in time. The fluctuations occur, but large amplitude fluctuations are very unlikely, so the macro state does not tend to change in time very much. Then we call the system in equilibrium. All right. So this is going to be the defining factor for equilibrium. I have reached a state in which the number of molecules on the left and the number of molecules on the right are more or less the same, and the fluctuations do occur, but they are very small fluctuations. Large fluctuations are very, very rare because the probability of getting an ordered configuration is very small. Now, when I look at the fluctuations in time, so how n changes as a function of time, basically I want to talk about how I define the time average of n. So how do I define time average? Let's say that I have I'm taking a picture of these of this system from a certain time t equals to 0 to a final time t final, and I'm doing this in some time steps of delta t. So delta t, which is the time interval between ti plus 1 and ti, is tau 0. So every tau 0 seconds, I'm taking a picture of this system so that the total time in which I'm doing this experiment is m times tau 0. So my initial time is t1, then I have t1 plus tau 0, t1 plus 2 tau 0. And finally, I have t1 plus m minus 1 tau 0. That's the final time. So initial time, final time. Okay, so that means I'm taking m measurements of n. So how do I define the average value? I use this brackets and it's a time averaged over time tau. Basically, I have to find the value of n at time t1, then I have to find the value of n at t2, and then n at tm, and I divide it by the total number of measurements I make, m. This is going to give me average value of n in time. So that's just a arithmetic average. It is 1 over m, sum over I equals 1 to m, n measured at time in at times ti. All right, so if I look at this definition for discrete times, time average of n is 1 over m. I multiply it by the time interval delta ti, I equals 1 to m, n at ti, which is also multiplied by delta ti. And remember, I defined delta ti to be tau 0. The time interval is the same, tau 0. At every tau 0 seconds, I'm taking a picture of this experiment and counting the number of molecules on the left, and then I'm taking the average over the total time interval tau. Tau is m times tau 0. Now, as this tau 0 gets smaller, becomes dt, let's call it dt prime, what happens here is this is going to approach in the continuous time limit an integral 1 over m times delta ti, that is m times tau 0, 1 over tau, integral over time from time t to t plus tau, n of t prime dt prime. So this is going to be, for continuous time, the time average of n averaged in the time interval tau. Okay, so that is time average for continuous time. And for discrete time, the time average is 1 over m, sum over I equals 1 to m, n ti, where I have delta ti is equal to ti plus 1 minus ti is tau 0, and the total time tau is m times tau 0. So that will be the time average value of n for discrete time. Okay, finally, I would like to quantify some of the things we have discussed here with an example. So let's give an example, numerical example for this experiment. I have a box with volume 1 centimeter cube, that is 10 to minus 6 meter cube. The pressure is 1 atmosphere. P is 760 millitorr. That is 1 atmosphere, and 1 atmosphere is 1.01, 10 to 5 pascals. Okay, and this gas is at room temperature. So the temperature is T is equal to 27 degrees Celsius or 300 Kelvin. And the universal gas constant is 8.31 joules per mole Kelvin. So how many moles of gas do I have? Well, since this is an ideal gas law applies. So I have pressure times volume is equal to number of moles N RT. So let's make this nu. Nu is number of moles, not to confuse with N, the number of molecules on the left. And I will find that this number of moles is 1.01 10 to 5 pascals times 10 to minus 6 meter cube divided by universal gas constant times 300 Kelvin. I will find 5 times 10 to minus 5 moles. And how many gas molecules is that? 1 mole is Avogadro's number of gas molecules, 6.02 10 to 23 molecules. Therefore, I have N, capital N, the number of molecules inside this box is number of moles times Avogadro's number. So it is 5 times 10 to minus 5, 6.02 10 to 23. So this will be roughly 3 times 10 to 19 molecules. Now, how many configurations do I have? Possible configurations do I have? In this case, it's going to be 2 to the power 3 times 10 to 19. So 2 to the power 3 is 8. So that's going to be 8 to the power 10 to 19. So that's approximately 10 to the power 10 to 19. Okay, so I'm just doing an approximation here. Let's look at the age of the universe. Age of the universe is actually 10 to 10 years. So I have 10 to 10 years. So that's going to be 3.15 10 to 7 seconds per year times 10 to 10. 3.15 10 to 17 seconds. So what is the probability of having no molecules on the left hand side? It is 1 over 10 to 10 to 19. What is the probability? This is 0. So it's almost impossible to have no molecules on the left hand side if you have 5 times 10 to minus 5 moles of gas inside this container. So that's a very ordered configuration. Ordered configuration is unlikely. The probability is approaching 0 as the number of molecules becomes very large.